Hello and welcome to In Control, the first podcast on control theory. Here we discuss the science of feedback, decision-making, artificial intelligence, and much more. I'm your host, Alberto Padoan, live from a recording studio in Zurich. Quick thanks to our sponsor, the National Centre of Competence in Research on Dependable Ubiquitous Automation and the International Federation of Automatic Control. Our guest today is Tryphon Georgiou, distinguished professor at the University of California, Irvine. Welcome to the show, Tryphon.
Thank you, Alberto. Thank you very much. It's a pleasure.
So Einstein once said, imagination is more important than knowledge. So today we're trying to explore how knowledge leads to really groundbreaking scientific discoveries. In doing my usual deep dive into the topic, I went down many rabbit holes looking at your research. I saw that basically there are all the basic ingredients of control theory in your research trajectory, the interplay between data and models, resolution, robustness, metrics, limits on performance, all the way to the arrow of time, non-equilibrium thermodynamics. So I hope I'll do justice to your body of work today.
Thank you, Alberto. I was very happy and privileged all my life and career to meet good people, learn and continue learning. And this is sort of a result of that, I ended up following a number of directions.
Yeah, I mean, it was a really incredible research trajectory, but maybe before we jump into the scientific conversation, I thought maybe we can mention some of your passions. So I was looking at your interview on People in Control, and I found out that you are a very fond runner, apparently. You run,
Thank you.
According to that record, at least 17, so larger than equal, 17 full marathons. Is it?
Yes, that's exactly the number. Yeah.
Okay.
It's a Fermat prime. I think I'm going to probably run a couple of more, though I've slowed down. The marathon running was kind of a midlife crisis. So there was a time that I sort of, initially as a kid, I was not a runner. I liked other things. I liked ping pong, swimming, soccer, but I never ran long distances.
It's something that you picked up
and
later.
Then I sort of heard some friends who were running the marathon here and there. And Minneapolis has a tradition. Every year there's the Twin Cities Marathon. So I thought to myself, this is a challenge. I'm just going to run it once. And in fact, the first time I didn't even prepare. So, in fact, I was walking, to school, and I was with Alan Tannenbaum. And I remember he says, any plans, etc. I said, I'm going to run the marathon pretty soon. He said, when? 6-7 months? I said, oh, my schedule is much shorter. So it was like a month. So I started training right before. So the first time it was kind of a disaster. I finished, but it was mind over matter.
Okay.
And I only intended to run once. But then I got addicted. And
it's already a miracle to finish a marathon
I finished the
with
first
1 month of training.
The first time I finished in 5 hours and 7 minutes.
It is huge.
It was okay, but it was pain. Then after that it became better, and my time was usually around 4 hours.
Wow. Okay.
And the last time it was in 2015.
Okay.
Right before going to California.
Because the weather in California doesn't encourage.
Exactly. No, it worked the other way around. Like in Minneapolis, so because the winters are very long, and you don't have a chance to exercise. Sometimes I would run indoors. There were some exercise machines and so forth nearby. But then whenever there was a reprieve from the weather, I would get dressed and I'd go around the lakes, very long distances, like an hour and a half, sometimes 2 hours, slow and every couple of weeks, 1 week, something like that. And when I went to California, I thought to myself, now the weather is perfect, I'm going to run every day. So it worked the other way around because I can postpone it for the next day and for the next day. So I ended up sort of running shorter distance now, 10 miles and so forth. Then in my early years, by the way, in Gainesville actually, under the influence of Alan Tannenbaum, I used to be going to the gym.
Ah.
So it was kind of a different exercise at the time.
Despite the humidity.
Yeah, in spite of the humidity. Yeah.
Actually, maybe we can talk about that. So, because that really relates to how you started into the field of control theory. I was reading a beautiful passage of this interview on people in control, whereby apparently you received a letter from Thanos Antoulas, and you mentioned that you still keep that letter that basically convinced you to join the center in Gainesville.
Absolutely, yes.
Of course, the center was held by Rudy Kalman, pioneering figure in the field of control theory, inventor, of course, of the Kalman filter. So how did it all start?
So when I was finishing the National Technical University of Athens, I knew that I was going to do something that's mathematical. I finished mechanical and electrical engineering. My degree was in both disciplines. It was a 5-year program. I always loved physics and mathematics, and I was at the last year sort of looking at different directions. So one of them was control, the other was information theory. So I was debating between the two. I was accepted actually also at Cornell, and most likely I would have worked on ray distortion theory or something like that if I went there. Then I was also accepted in several other places. Maryland was another one I was considering. Then at some point I got a call from Thanos because I had contacted Kalman, and Kalman wanted he was coming to Athens, Thanos Antoulas, he had family there, and he wanted me to be vetted by Thanos. So we met at the Hilton Hotel downtown in Athens. And we sat down, and I still have a page where he tried to explain to me the range of ideas that relate to system theory, mathematical system theory. There's algebraic structures, some infinite dimensional systems, and so on. And I was convinced at that moment to look into that, and the rest is history.
Was that something that you came across? So those subjects, you also came across them during the studies in Athens, or?
Definitely. I looked at, we had a subject of control. We studied certain topics in control. Also, information theory was very close to my heart.
Yeah. I mean, you managed to walk a very fine line over the years.
I ended up doing both in one way or another.
Yeah. So this convinces you to take the plane, and as we were mentioning in our conversation before recording,
and land in
September 1st,
Florida.
1979.
Exactly. It was very interesting. So I flew into Gainesville. It was just past midnight. And then I step out of the plane, and as soon as I step out, I feel this very hot, warm air coming towards me. And I thought it was the turbine of the plane. So I thought how silly it is to design it so that you step out in front of the turbine. Then I looked to my right to see it, and there was no turbine there. So all of a sudden I realized I'm in for a interesting time there. It was very warm, humid, the summer. And typically the summers are like that in Gainesville.
And so I'm actually curious about how was the environment at the center, because it has sort of a legendary status almost.
Yes. Oh, the center was a unique place. Kalman would be there probably a few months every year. At most, I would say 5 months at the time. Coming in and out, he would spend most of his time in Zurich. But in spite of that, the center was extremely active. There were a lot of visitors coming through, giving seminars when Kalman was there, sometimes even when he was not. I met practically everyone in control, Sanjoy Mitter, Roger Brockett, Tom Kailath. It was a continuous string of people. The center, at the time I joined, there was Pramod Kargonekar. He was my classmate and good friend. He graduated ahead of me, and to some degree he was mentor to me, as was Alan Tannenbaum, who came later on as a visiting faculty.
You already mentioned a huge string of legends in the field.
Yeah.
Incredible.
And there were a couple more students at the center, Bülent Özgüler, a very good friend of mine, and he's now in Ankara. Then a postdoc, Earl Emre, and later on Jacob Hammer, and Jaime Ribera, another student. He went back to Spain. And Fumio Hamano, who was working with Giuseppe Basile. There were a couple of other faculty there. Giuseppe Basile was a very, very good friend and also mentor. He passed away in an airplane accident. And he was quite a creative person. He created a nice geometric theory.
Every person that you mentioned so far was quite creative, at least according to my standards.
The level of osmosis, let me put it this way, was significant being there. The other thing which I really took advantage of was Kalman's library. So the study was, they had a couple of tables and it was surrounded by stacks of books. And the stacks of this library, they had small sort of partitions so that the books don't fall to the side. Mm-hmm. They had their proper place, Library of Congress classification and ordering of the books. And we were responsible for putting them back. Actually, one person was responsible every time. So one year was Pramod, then a couple of years it was me, and then, whoever.
Sure.
And at the end of the day, I think it's not an exaggeration to tell you there were like maybe 10,000 books or maybe more, maybe more. There's also a collection of preprints and reprints, and all of those had their place. And there was a very nice classification system that for the preprints and reprints, it was Kalman's sort of design. For the books, it was LC classification, Library of Congress. The secretary would ask for a sticker that was placed to the book and had the correct place and everything.
So it was basically, on top of being very valuable, also almost a competitive advantage.
Absolutely. I mean, the books were right there. So just sitting and absorbing everything. And we were exposed to many different things, from mathematical physics to algebra. I still remember where the books by Birkhoff and Serge Lang were. In fact, with Pramod, I'm just sort of going now to a more personal thing.
Sure.
With Pramod, we're playing a game. We would close our eyes. One of us take a book out of the shelves, and the other one, with closed eyes, is supposed to find the place and put it back.
Wow.
Because he more or less knew where they were. The book next to it was thicker, and etc. And also playing games with remembering first names of authors. And so it was quite an interesting, playful time. And at the same time, we're exposed to a number of
branches of every subject, basically.
Yeah, I remember Kalman, for example, he would invite people interested in neuroscience one time.
Nice.
It was a rich environment in every respect.
I was about to ask you something related to, your PhD thesis, which I'm certainly going to do. But before that, since we touched on the subject of creativity, how do you enhance creativity, especially in a place like the center? How should one do that? And I think this would be great advice for any research group, I imagine.
I think you, first of all, have to be exposed to ideas and be allowed also to pursue your own ideas. Have a sense of freedom in what to pursue. One shouldn't have the pressure to produce. The pressure has to come from within.
Okay, but how do you say, marry that, if you want, with the status quo, if you want, where this pressure is actually there? I
think right now, this day and age, things are becoming a little bit more hectic, I would say, because there's the competition for producing and writing papers is more. Back then, it was a little bit more relaxed because you were not expected to have X number of papers every year. Mm-hmm. So you could work on a subject for a significant amount of time.
And get to the bottom of it.
And get to the bottom of it, yes.
Yeah.
Yeah, basically the important thing is sort of to experience at some points those moments, those aha moments when you realize something, you have suddenly a moment of clarity. And then it's addictive. And then
I can imagine.
You keep going. And luckily, if you're in the right place with the right people, this continues for a lifetime. And it's beautiful.
I can imagine. So maybe we can actually start talking about the subject of your PhD thesis. So
yes.
The title would be Partial Realization of Covariance Sequences. I guess it would be nice to our audience to explain what is the realization problem, what is the covariance extension problem,
yes.
and maybe just give a bit more details about the outcome of your thesis.
Absolutely. By the way, I wanted to say a little bit before that. So
sure.
My first work, so I went there and there was Pramod and the legacy also of Eduardo Zonta, who was there before, on Errol Emre, and they were interested in algebraic system theory. So I worked on a geometric problem of designing controllers and to reconcile a state space technique that was due to many people, and there was Morse and also Basile and other people where the concept was some invariance. So you try to isolate disturbances from affecting the output. There was a very beautiful framework, and there was also the polynomial approach that predated those techniques, and we tried to reconcile this. And I will tell you why I'm starting with that. And that gave me the opportunity to be exposed to a really beautiful subject, which is called the polynomial model. It was basically introduced by Paul Furman. It has its roots in earlier theory on realization of systems. So the polynomial model basically characterizes the state of a system as a remainder space. You have, let's say, a transfer function, you have an input. Think discrete time. So the input, you think in the Z transform domain, so it's just a polynomial. So the system remembers only the remainder when you divide by the denominator polynomial of the transfer function.
Okay.
And the remainder is the state.
Okay.
You can truly characterize this as a space of remainders, and you can do this in multivariable. And that was basically explored in mathematics. There were some models for operators going further back. So I'll come back to that a bit later, because this is very important. So anyway, we worked on this paper, and when this was finished, at some point, I remember I was sitting in my office, and then Kalman comes in, and he says, I need to talk to you, he says. I know what you're going to do for your thesis. And I said, what? Because I was doing algebraic system theory. He says, I want you to do stochastic partial realizations. Okay. And then he leaves. His flight to Zurich was the next day or something, so I had no idea what he meant. He didn't really explain. So then Jaime Ribera, he said, well, I think I know what he meant. He just wrote a paper. And he wrote this paper, it was called something very similar, Realization of Covariances, for the Toplitz's Memorial Conference in Tel Aviv, which he was going to present it there. And probably that's what he meant. So then I looked at that paper and I started studying the context of how to formulate the problem. So let me explain what the problem is. In system theory, one sort of model for going from input-output response to state space is you have, let's say, the impulse response. And the impulse response corresponds to a transfer function and corresponds to a state space representation, if the system is finite-dimensional. Now, if you only know a partial segment of the impulse response, then what do? That's called the partial realization problem. You have finite impulse response, so you're listening to the echo from banging a box, because that's the impulse response, for a certain period of time, and you want to find the structure inside the box. And there's a beautiful and well worked out realization theory that is based on the structure of Hankel operators. So you look at sort of a Hankel operator, you look at the rank of it, and as you increasing the input, the data that you're getting, what's called the Markov parameters, the rank may jump, may become higher. And depending on those jumps, you can find out what's the minimal realization. In other words, minimal realization means a state space model of minimal dimension.
Yeah.
So, but this has absolutely no constraints on the system. So the stochastic realization problem is to do exactly the same when the impulse response has some sort of positivity constraint. In other words, the impulse response is a covariance function of a time series, discrete time, for example, or you can have it also continuous time. So you're observing sort of a time series and you would like to get a model for this. What does it mean? If it's a stationary time series, you need the power spectrum. Alternatively, you want a model that will generate this time series or something statistically equivalent if it's excited by white noise. The only thing that you have available is some correlations that you can make on the fly. So this is exactly your data. So it's a partial covariance. So then, knowing this, you would like to know something about what models can explain the data you're observing. And you would like to do it in a way so that you can recursively enlarge the size of your model to take into account the new data that you are receiving. So Kalman had worked on the realization problem without any constraint. And in that paper, in the Topless Memorial Conference, he tried to work out what happens if you have a constraint of the response that you're observing is just simply a sequence of covariances. By the way, this subject has connections to classical moment problem, to going all the way back to 1910, Kara-Theodori, Feye, Rees, and to analytic interpolation theory. Nevanlina, Peak, and all of that. It's very, very closely connected. It's in some ways what's called the moment problem.
Yes.
So the moment problem is exactly that. You are observing moments of a distribution, and you would like to say something about the distribution. Now, the added feature here is that what you want to say has something to do with a degree of an underlying model. And you would like to be respectful to that. You don't want to inflate the degree just for your convenience. So Kalman tried to work this out, and he basically worked out the degree 1 case, which is almost trivial. The way he posed the problem made it a little bit, this is very difficult to explain in words, but it made it a little bit more complicated than it should have been. And in that paper, so he comes back in December, and he asked me, this was in the summer when he told me to work on the subject, and I studied moment problem, theory of orthogonal polynomials, Zigo, all of this is very related.
Everything that was connected to the problem.
Everything that was connected to the problem, and I already had some initial contributions. And I wrote a little paper. Actually, that first paper went to a conference, and it was jointly with Pramod. I was talking to him all the time, and you know, he initially we were learning the subject together because he was interested as well. So he comes, Kalman comes in December, and he asks me to, you know, to see what I did, and I said I realized that this, you know, your sort of idea for my thesis relates to exactly the topic of your paper. He said, yeah, of course, he says. And he had this way of saying, yeah, I know, a very kind of sharp way. And he says, did you read this paper? I said, of course, you know. So I said, what did you think of the paper? So I was in his office, and I started explaining something on the board, and I said, I think it's very interesting. However, I say, I think the formulation is a little bit problematic. At the time, I was my early years, I was a bit timid. So I wouldn't come across as very sort of forceful and determined. So I was a bit shy, yeah. So Kalman didn't probably believe me that there was a problem with the formulation. So he just kind of dismissed it. So he said, no. He just, even though I explained to him some things I've done. So anyway, that was a very brief meeting. And then he leaves. A week, 2 weeks later, he left. And we didn't have a chance to talk more about this. Then he comes back a month, 2 months later, and then I have a chance to discuss it. And I had already written a report exactly on what he has done and why I thought that this was not okay. And so he was on the phone and he showed me the boards. I remember I stepped to the board and I explained and I write down. So he was listening because he was trying to book a ticket. And then he turns his full attention on this. And then he realized that there was an issue. And he was not very happy. Because his paper already went to the printer. And he says, why didn't you tell me this in December? I tried. So anyway, so the problem was, now it's very hard to explain, but he kind of shifted the starting point of the time. Instead of at 0 to 1. And that make a difference by 1 on the degree. So he thought he was dealing with a much more complicated second or third degree situation, but it was actually degree 1. So it kind of became trivial. And his derivation supposedly was very long. He didn't have the full details in the paper, but it could be done much, much simpler.
Okay.
So anyway, so then I continued working on this and kind of reformulated in a different way because it was a very hard semi-algebraic problem to find the minimum degree. Again, you have partial data and you want to reconcile this with something having to be positive. So I realized that the degree n, which kind of is commensurate with your data, is a very nice class of models that you can look to find the structure there. And I parameterize all the solutions stratified by the size of the sequence. And it turns out that it has a beautiful nonlinear parameterization. In other words, now, I don't know how technical I am.
Well, we can go as technical as we want, but I think maybe I'll make an effort to try and simplify this concept. So you are given this data, you populate them into, say, a matrix of a given structure, let's say a Toeplitz-Henkel matrix with our covariances, and we're basically trying to fill in, it's a matrix completion problem. We want to fill in an infinite dimensional matrix,
yes,
let's say in discrete time.
Keeping the degree small.
Keeping the degree small.
Which is technically very difficult.
Yeah.
Let me explain the problem in the following way. So suppose you have a discrete time series and you have the autocorrelation function up to some order, let's say n.
Yeah.
If I ask you to have a degree n model that explains the data, there are several models like that. It can turn out that there is no model of degree n minus 1. So the first size of models which is guaranteed to be non-empty is degree n.
Where by degree you're thinking of rational transfer.
Rational transfer function, rational extensions of a certain degree. In other words, you're looking for an ARMA model, autoregressive moving average model. So it is very standard and goes back many years to look for an autoregressive model. So if you have a degree, sort of a autocorrelation function of degree n, you can always find an autoregressive model of degree n. And this is called the maximum entropy solution. So what I was interested in finding all the possible models that are consistent.
Yes.
Now, if I tell you to find an ARMA model of degree n, numerator of degree n or less, denominator of degree n or less. If you choose the poles of the denominator, it's possible that you cannot reconcile the numerator to match the data. It turns out that there is another polynomial which has to do with spectral factors, which is completely free. If you choose that one, there's always a solution that's going to match the data. So there is a beautiful parametric description of all degree n solutions.
Is this what now goes down in history as the Georgiou-Kimura parameterization?
No.
No, this is something that we will talk about later.
That's different. So what is the, in fact, Anders and Chris Burns called it Kimura-Georgiou.
Okay.
The Kimura-Georgiou parametrization, or whatever, is a very simple lemma, algebraic lemma, which I used to prove some other results. So I had it in my report to Kalman and my thesis, preliminary things much before. This is a very interesting story. It's a long story here. So it's a parametrization of extensions without the positivity constraint. Mm-hmm. It's purely algebraic. Mm-hmm. You choose something and then you fit something else so that it matches. Mm-hmm. No semi-algebraic constraints. But it has a very nice structure. There's a very symmetric, nice structure. And then somehow this, piqued the interest. Kimura came of it independently. Actually, Kalman was explaining to him this direction in Switzerland. And then at some point, he had a independent derivation, which was a little bit more complicated. He published this, and mine, I think, is only in my thesis. It's a little lemma. And it's an interesting story. It's completely different. The other one is analytic. The other one has the proof of it is topological, using degree theory to show that a certain set of nonlinear equations has always a solution. Yeah. And the proof in my thesis proved existence of this parametrization. I couldn't prove in full generality uniqueness, only up to degree 2. And then it took several years, and then Chris Burns and Anders Lindquist teamed up.
Definitely something that I want to touch on.
Yes.
Because it also awarded you one of the Axel B prizes. Yeah. And it's a beautiful subject and a beautiful paper that I really want to dig into.
But the story of the main kind of contribution in my thesis is that I had the existence. I didn't have the uniqueness in full generality for the covariance extension problem. And then it took several years, and Chris Burns and Anders Lindquist teamed up with a couple of other people, Gusev in particular, and they came up with a proof of uniqueness, which was refined later on, and then we joined forces, and there's more development. But the starting point was this parametrization in my thesis in terms of what one could refer to as the spectral zeros.
Yes.
So you try to find all the extensions based. If you choose the spectral zeros, then you have an extension. Mm-hmm. If you choose all the spectral zeros to be at the origin, you have the maximum entropy extension.
Yes.
And it's a nonlinear parametrization. It's a very interesting, very, very, and it's quite non-trivial. Now, let me mention this because you mentioned about Kimura. This was in the last year of my PhD, and even though I explained this to Kalman a couple of times in quite a bit of detail, and the year before I had written a very lengthy report with the proof and everything, and I sent it to him, and he came to Gainesville and I explained it, but somehow Kalman always liked algebra. So there was a little bit of a sort of misalignment there. And I remember one time that he said, okay, this is good. It's quite good, he said. But there should be an algebraic proof. So, I was again very shy. So you have to put this into the picture. Yet I turned to him and I said, but Professor Kalman, even the fundamental theorem of algebra doesn't have an algebraic proof. It's topological. So he kind of was taken aback. So, I didn't agree with him, but normally he's okay, but you have to come a little bit forceful and to explain more. And I was, so anyway, that went down in a certain mixed way. And then later on that year, actually in the spring, I think early spring, it was, I think it was in 83, early February maybe. So he had organized this US-Japan conference in Gainesville, and he invited who is who in control from the US side and many people from Japan. And I remember all the names that I mentioned before: Roger Brockett, Sanjoy, S.Y. Kung. He was at the time working on with Tom Kailath, and he was also working with some people in Europe on Hankel approximation. They were all there. And from Japan, there was, of course, Hidenori Kimura, he's a good friend. I really, kind of connected with him. So he came and he was going to present this algebraic result. So this was on a Thursday when they arrived, and he was going to present this on Monday. So then Pramod realized that because he saw the abstract. So he said, he's talking about this lemma in your preliminary thesis. And he told Kalman. So then Kalman comes, and it was Thursday night. He comes to my office, says, Saturday I'm teaching, I'm going to give a presentation from 9 to 10, and I would like you to present about your results 10 to 11 on a very short notice. He didn't tell me what he wanted me to present. So, fine, I prepared, and then he finishes his talk, and then I start explaining on the board. And I discussed the thing I was most proud of, which was the nonlinear parameterization. So I didn't even touch that lemma. So at the end, he realized that, I don't know, he probably wanted an exchange between me and Kimura. And then he asked, he said, okay, so how about that lemma? And I said, what lemma? Because I had several lemmas. So he said, that one. I said, okay, I understand. Professor Kimura is giving a lecture on Monday. It's an algebraic result. And, I sketched on the board. And I said, I can give you the proof. My proof is like this. And I just explained it. And, I was very courteous. And Hidenori was just sitting first row there. And he was happy with the way I explained it. So nothing happened. So Kalman wanted a little bit more action. And then he started sort of challenging other things I said before.
Okay.
And there was an interesting exchange.
In non-technical terms, he was grilling you on the board.
Yeah, he was. he kind of, I think he wanted a little bit more of a
collaboration.
Or not collaboration. He wanted a little bit of
action.
To put it that way. Yeah. So anyway, that went finished like that, and in fact, he challenged me on some things, and I said, about steps in the proof. I said, here's the proof. I can repeat it, and so forth. And it was quite an interesting experience. And in some ways, I feel at the time, I was very intimidated because he was sort of came over very, very aggressively. And in fact, Alan stood up and he said, we've seen the proof many times. And I also repeated it there. But that was a very interesting lesson for me because I had to stand my ground. Mm-hmm. It was really the first time that I felt that I really needed to defend myself. And
this is a story where topology comes to the rescue, basically. So topology is somehow...
Yeah, it's basically from a subject called nonlinear functional analysis and a degree theory. Basically, you try to find a way to ensure that a certain set of nonlinear equations have a solution. And you have algebraic and semi-algebraic constraints and all that.
Yeah, I was just about to say that this is a recurring theme in your research, and we want to talk about it also later. Actually, there's way too much to talk about, so I'm going to try to speed up the pace and try to cover other subjects.
Yes.
The only last comment that I want to make on your PhD thesis I found very interesting is this relationship between positivity and somehow physical quantities, so manifestations of physical processes somehow. There is a nice passage in your PhD thesis where you say, and the reason is that positivity is in one form or another intimately related with manifestations of physical quantities and entities. Do you have any thoughts about that?
Yes, the whole edifice of probability theory, the positivity of this experience of having frequencies. You cannot have negative frequencies. We can come back to this after a bit later because
I saw some late papers that are
yes,
challenging this.
Yeah. No, the constraints are, positivity constraints are quite ubiquitous. And I want to mention the subject of positive systems. So one thing that has to be said is that sort of Kalman, from early years, 1960, 62, 63, etc., he shifted towards this algebraic system theory and state space controllability, observability. And we all teach that at the graduate level. And the main theorem there is that if a realization of a state space is canonical, meaning controllable and observable, then the size of the state space is minimal. It's the smallest possible that can explain the transfer function or the impulse response or the data. So he was very fixed about this correspondence between minimality and some sort of canonical structure. So to some degree, he tried to, and he invited his students to work on this. So for example, Eduardo Zonta worked on polynomial response maps, which in some ways was trying to capture something similar.
Yeah.
And then Yutaka Yamamoto worked on infinite dimensional systems, again, trying to get a bit of the same structure. How do you characterize minimal realizations? So, and he asked me to look at the stochastic setting where you have a positivity constraint. But the problem with the positivity constraint, you have these semi-algebraic sets that basically destroy the linear structure completely. And that was not quite realized at the time. Mm-hmm. Now it's evident, and many people have understood this also in the context of positive systems. So let's say you have some system that represents population of some, and so you have to have the state evolving in the positive cone.
Yeah.
So to have that, then you have some constraints on the A matrix of the state space model. Yeah. So it has to be positive. So the simple question is this: I give you an impulse response, which is positive, and I tell you find A, B, C, D realization, which they're all positive matrices. What is the minimum size of A? So the answer is, even if the sequence is rational, it could be infinity. You might not be able to have a finite dimensional model for that. So the positivity breaks completely algebraic structures. It makes the problem very hard. So to find out some nice parameterization, it was a stroke of luck in that setting. Yeah.
Maybe this is a good time actually to move on to your next steps.
Yes.
So then, after graduating, I see that you continue, as you say, working with Pramod, and you moved to Iowa in 1986.
Yes.
And according to my records, of course, it will be difficult to do justice to every single contribution that you've made, but something that definitely piqued my interest was the paper in 1988 on the computation of the gap metric. Because there you really start working almost on a new line of research that has involved quite a lot of your work over the coming years.
Yes.
And I was wondering whether it's fair to summarize that the outcome of that paper as that it was actually easy to compute the gap metric, but until then it was not known.
Yes. So let me wrap up a little bit the work before.
Yeah.
So coming out of my PhD, I had this contribution, some understanding of the moment problem. And there was a segment of the work relating to spectral factorization and also to certain filtering algorithms. And then I had several papers, some of them with Pramod, some by myself, on fast methods for doing spectral factorization. And this is sort of a derivative of my thesis.
Related to covariance extension problem.
It relates to that. Now, what I realized there is that there is a connection to nonlinear peak interpolation. So the background of my thesis, even though I was doing nonlinear function analysis and some other things, but in the background there was a problem that was kind of equivalent to the H infinity problem. The covariance extension problem is not much different. It's a moment problem, both of them are. So it was very easy for me to transition to understanding sort of the mathematics of nonlinear peak interpolation and operator theory, with Fourier's coming into the picture, and the Compton lifting theorem. To some degree, all of them are very connected.
Yeah. Because all of these are essentially interpolation problems.
They're interpolation problems, yes.
For complex valued functions with complex valued data, subject to certain constraints.
Yes. In fact, the problem is much simpler. All of these sort of buzzwords, maybe they frighten younger people that come into the subject. The subject is absolutely trivial. Like, if you have interpolation data and you want to ensure some analytic constraint, the key thing is you can do it recursively. You take the first piece of data and you see, is this okay? Then you take the second piece of data and you try to see, can you match the two things with a structure that preserves your constraints? And invariably what you get is you get a quadratic equation. So the quadratic equation is satisfied for one solution, let's say, and for a ball around. So this is called the one-step extension. So there's a nice sort of recursive solution of all the moment problems and all the nonlinear peak problems and so on and so forth. Now, there's another piece of the puzzle which has to do with, again, I'm not going to expand on this very much, this realization theory of Fuhrman. This polynomial model, what I would describe as remainder space, which is a modern operator theory. So all of this ties together. So then I come out of my PhD thesis and I know quite a bit of this functional analysis. So I was looking for new problems. So I was in Iowa in my second position. My first position was at Florida Atlantic University. I was there for a couple of years.
Okay.
And then I was for 1 year visiting faculty at Minnesota, and from there I went to Iowa State. So Iowa State, it was more of a research institution. So I was, because my first appointment, I stayed in Florida, my wife was still in Gainesville, and I stayed nearby. I was looking for a position at the time. There were not positions in the summer, and the time was short, so I started there.
Yeah.
Then at Iowa State, I was looking at interesting problems in robust control. And the gap metric piqued my interest. And again, this was a bit of a stroke of luck because I had the right background and I was looking at it and I was very determined to understand it. I'll tell you a little bit about the gap.
Yeah, let's do it.
Yes. So the gap metric is a very, very simple idea. The roots of it go back to 1947. There was a paper by Belas, and another paper by Krein and Krasnodębski at the same time, 1947. So they were interested in invertibility of operators. So they came up with a natural metric for operators that if you have an operator which is invertible, then if you move a little bit in this metric, nearby you always ensure that the perturbation is invertible. There's a beautiful book by Cato that studies this.
Yes.
So now this came to the attention of George James. I think the story is, George told me this some time back. He said that his student, Ahmed al-Sakari, was talking to someone in the math department. They were interested in understanding invertibility of systems. So he somehow this came to their attention. They looked at it. And James and Sakai wrote a conference paper in 1979. The importance of having a natural metric, and I'll explain what this metric is, it was evident because, you see, when you compare systems, you need to compare a stable with an unstable system. You cannot say that the distance is infinity, because both of them, where they are within a feedback loop, they could both be stabilized and have very similar response. Suppose that you have, let's say, an integrator. The integrator you stabilize with negative feedback, let's say. Now, you really don't care if the pole moves a little bit to the left or a bit to the right, because if it's within a feedback loop, you can't tell the difference.
Yes.
So it's very important that you are able to compare systems of this type, stable and unstable at the same time. And so this kind of questions came to the attention, for example, of Sagar. And Vidyasagar wrote about the graph metric. The graph metric was not computable. But he basically was interested to show that you can metrize the space of systems in a suitable way. So I forget, his paper was 1982, something like that. And then Georgia's student, Ahmed al-Sakari, he kept working on this. He wrote a couple of papers, but was not able to make progress. He was working for systems of order 1, basically, and some of the technical setting was not quite right. We commented on that in a subsequent paper with Malcolm that we wrote. We can talk about that.
Definitely.
So this work was 1980, I think 85. So somehow the gap metric was thought not to be computable. It was an abstract concept. You compare two operators in a certain way. So it was kind of abandoned. I always liked geometry from my high school days. So when I looked at it, and then I saw the original paper 79 of George James, which have the definition which goes back again to Cato and all these people, it looked to me very geometric, so I needed to understand it. So I started working on this, and in fact, it was very quick. It was within a week that I finished, and I typed the paper, and I sent it to some control letters.
Which is a delight to read, by the way. There will be a link in the description of the episode. Yeah. It's just 5 or 6 pages, so super short.
It was extremely short. So let me tell you what the gap is. So let's say you have a 2x2 matrix, and you ask the question, is it invertible? Of course, you take the determinant. Now, and if the determinant is not 0, you can invert it. But not so fast, because let's say it could be one eigenvalue is very small, the other eigenvalue is very big, right? So maybe it's invertible, but not quite invertible, because a small perturbation of the elements can make that eigenvalue 0, right? So the determinant itself doesn't quite capture it. So you ask yourself, okay, what is the story? I have this matrix. It has 4 entries, A, B, C, D. Let's say A, B is the first column, C, D is the second column. If you think about this, what a very important quantity is the AB as a vector and the CD as a vector, how close they line up. So you look at the angle between these two vectors.
The image space and how far is...
Exactly. This angle, the sign between these two vectors is the gap. So the gap is nothing more than the sign of an angle between two subspaces. And this could be finite dimensional, or they could be infinite dimensional. So when you have 2 dynamical systems, and you don't need these dynamical systems to be of the same order. One could be infinite dimensional, it could be finite dimensional. Let's think linear. Mm-hmm. How do you compare two systems? Let's say you have your system and I have my system. How do you compare them? You can play a game. So I choose an input that generates an output for my system. And then it's upon you to choose a different possible input for your system to generate a different output so that your input-output pair is very close to my input-output pair. So if the behavior in the language of Willems is the same, in other words, your input-output pair is very close to mine, and you can always do that, then it means that I can't tell really the difference if they are within the same stabilizing feedback loop. So it's very nice to understand the gap in the time domain. The paper and most of the subsequent papers are in the frequency domain, and they require a lot of math that I'm afraid sometimes they become less accessible as the year go by because they're built on a certain culture of the time. But the intuition is time domain. You look at input pairs of one system and input output pairs of the other system, very much like you're going to look at two lines on the plane and you try to see the angle between them. The angle between the two lines, the line is a graph of an operator. The operator is multiplied by a number. So if I tell you y is equal to 5x, the line I draw is the graph, and then I have another line. So the gap is exactly the sign between these two.
This is because, again, in the language of Willems, linear systems are subspaces, and
they
therefore
are subspaces.
A natural way to measure distances between subspaces is through angles.
The angle, yes. So the gap graph robustness theory was developed at the same time. I think Willems at about the same time was having this sort of insight that has to look at behaviors. Behaviors are the same thing as graphs, right? The only difference is that in graphs, you're committed as to what is the input and the output. You know, when you talk about behaviors, Willems wanted to, and for good reason, to, somehow to push this aside. I mean, he used to say, who tells you what the input are and what the outputs are? And he was right. I mean, but again, it's very, very related. The mathematics is very, now there is a little bit of a subtlety in looking at behaviors. The issue of causality.
Something that I would really, really want to talk about later, because there's a series of papers that you wrote with Malcolm Smith that is amazing.
Yes, it was a little bit, there's a subtlety, which I always had very interesting discussions with Jan. I remember one time we were coming from India, we were on the same plane, and it was Saga's birthday. We had a celebration there, and they were coming back. And it was like 4 hours we were debating this, and maybe 3-4 hours on the plane. So anyway, that paper basically opened up the field, because the gap was a beautiful concept, and that paper expressed the computation of the gap as a problem in H infinity. So it was immediately solved and connected almost like a glove to everything else that Georgiou was doing at the time. And in fact, he was very complimentary. I sent him the preprint, and he sent me back a wonderful letter. And he said, oh, this is absolutely, remarkable, and I have great ideas how to pursue it. And of course, it was natural to start looking at the robustness problem. In other words,
now, given that you could compute this metric, it couldn't be used as an analysis and design tool.
And the analysis and design tool.
Yeah.
So, and then the continuation of the story was that George mentioned this, that he got this preprint from me to Malcolm. Malcolm Smith was a dearest friend. He spent some time at McGill, and he was working on some H infinity problems at the time. And then he had already accepted a position at Columbus, Ohio. In fact, it's very interesting because I met Malcolm at McGill before all this work. I was working on basically a periodic design of periodic controllers it's another story. Let's just leave that one because too many stories.
And there are many.
So then I met Malcolm at McGill at one of my visits. So I knew him, and I tried to get him to Iowa State. In fact, we made him an offer. And this was before we started collaborating, and then he decided to go to Ohio. So he was at Ohio State, and somehow he was in contact with George. And George mentioned to him that I had this paper that allowed computing the gap metric. And then he calls me up and he said, can I have a preprint? Because back then you couldn't download from the archive.
Yeah, of course.
And I sent him a preprint and he asked me, he said, what are you working on? And I said, I'm working on trying to find measures, how to design for optimal robustness. And he said, can we work together? I'm very interested. And I said, of course, because, the subject is rich. And this started, I would say, a most wonderful collaboration.
Certainly long-standing and very prolific.
It was, with Malcolm, we resonated. And in some ways, we had very similar tastes in problems and getting to the bottom of it. So we started working shortly after publication of my paper. And I visited him in Ohio. I think he visited me. And then this was, I forget, it was something like starting something around June of, I think it was 88, something like that. And then by December, we thought, okay, now we have a short paper. And within a month and a half, the paper was exploding because we could see, you see, this was one of those aha moments. You could see all kinds of connections.
Yeah.
Let me say another thing which it was quite interesting. At the time, computers were not that fast. And I remember one time I was visiting Malcolm in Ohio and we were typing the paper, which was 45 pages, not very, you don't have figures or anything, at least one figure at most, in LaTeX.
Wow. Okay.
In LaTeX, 45 pages,
yeah.
The preprint. And I remember we would have to have a printout of the paper, decide on what we're going to change, make all the changes, then press carriage return twice, and then go for a coffee. Because it would take 10 minutes of the mainframe to the LaTeX.
Incredible.
And if we had one little mistake, now you just LaTeX and LaTeX and LaTeX and LaTeX, another 10 minutes. Anyway, so that was the start of a very, very wonderful collaboration and friendship. And Malcolm is a dearest friend.
So this culminates in the paper Optimal Robustness in the Gap Metric,
yes.
1990, on transactions of mathematical control, which awards you an Axaby, together, of course, with Malcolm, where you basically show how to use the gap metric as a design and analysis tool
yes.
for feedback systems. I was wondering whether we can summarize that paper, maybe briefly, touching on
yes.
the conclusions of that paper.
So the conclusions of that paper are made even more. This paper has quite a bit of material looking at this problem from different angles. So it shows you how the optimally robust controller can be also computed with an H infinity problem. It gives you that sort of coming back to the description of the gap metric as an angle between the nominal and a perturbation. Now, you want to understand robustness of stability. So when is a plant and a controller sort of working together robustly? It has to do with, again, with the angle between the two. Because you need to invert some closed loop operator. So the optimal situation is when the two are perpendicular. However, the perpendicular graph to the graph of the system is not causal. So the optimally robust controller is the closest causal approximant to an ideal non-causal graph.
And thinking geometrically, this is a projection, is it?
It's a projection. Geometrically, let's say I draw a line on the plane, and then I just draw the perpendicular. This is very easy to construct.
Yes.
Now, the problem when you have dynamical systems is that the perpendicular is not a stable system. Mm-hmm. So then it amounts to finding a perturbation of this non-causal controller to a one which is causal.
Yes.
And this is extremely natural. It becomes, again, an H infinity optimization problem, which is equivalent, in fact, to what is called normalized coprime factorization.
Yes.
The model that you get out of normalized coprime factorization. In fact, this was a direction for design that was pursued by Glover and McFarlane. This was in parallel, and they built their framework on Vidyasagar was working on a very similar thing for graph robustness earlier. And in fact, he has a paper, Vidyasagar and Kimura, which was very instrumental in that. So Keith followed along that path. And because they didn't know what was a natural way to look at coprime factorizations, they tried to normalize as if that this is sort of a reasonable thing to do.
Yes.
Now, it turns out that this is not only a reasonable thing to do, it's a very natural thing to do, because this describes in an invariant way sort of the system, and all the geometry of the graph and gap robustness comes almost exactly like a glove, fits with that. But now you have, it's not like you do it because it's convenient. You do it because you have to. You know, it's
robustness optimization in the gap metric is basically equivalent to
normalized coprime factorization.
Yes.
The design methodology is slightly different. I mean, the rationale for this, and we developed it in parallel with Keith and McFarlane, but it's again very similar. And if you go to MATLAB, the normalized coprime factorization gives you, in fact, some of the code. I interacted with Gary Ballas when that was developing, and it has parts of code that
and you helped developing basically.
At the time, yes. In fact, the routine on the gap metric, I was contracted by Musin at the time to. Of course, I had it, so it was ready. So it's all kind of fits together as a whole, And the theory basically was refined in subsequent years to bring out more the geometric element. For example, we had some work, Malcolm and I, with Cyprian Foyos.
Yes, which I noted down gives you an Erdos number of 2, basically.
Yeah, yes.
You're one of the few in the field. I'm not sure how many actually have an Erdos number of 2.
Probably some, a few. I don't know. But it was also a very, very educational collaboration. Cyprian was a giant in mathematics.
Yeah, for our audience, I will just mention that Cyprian Foyos was is responsible for the commutant lifting theorem.
Yes.
It is used to prove many other results in interpolation theory, together with, I don't know how to pronounce it, Znagi?
Yes, Zinagi, Bella Zinagi. Again, I don't know how to pronounce it properly myself. Okay. I asked Cyprian one time.
So definitely a beautiful piece of mathematics that has to do a lot with H infinity.
By the way, there's also a paper by Saracen before. So Saracen is also credited with that.
Yes.
And there is a significant school of thought, the Odessa school in at the time, Soviet mathematics, which is was sort of very near it. But primarily the commutant lifting theorem is credited to Saracen and Nagy Foyos. And then there's also Rosenblum and Rovniak after that. But so just for the audience, the commutant lifting theorem is, again, it's not that frightening. The moment you understand it, it's very, very simple.
Okay. It is a bit frightening to me.
No, it's not. It's not. It's again a one-step extension problem. It's very much like the moment problem, that you want to add one more piece of data to fit a certain structure so that you don't destroy a norm. You don't exceed the norm beyond something. Look, think of it. There is a very nice equivalent almost formulation. It's called the parrot lemma.
Okay.
And you can explain it in extremely trivial ways, in fact, with high school mathematics. Let's say I give you a matrix, A, B, C, D, just a square matrix, 2 by 2 matrix. I give you entries for A, B, and C. And I ask you to find the last one so that the norm of the matrix is minimal,
Okay.
right?
Yeah.
For example, I could ask you to fit the last one so the norm of the matrix is smaller than 1. So to some degree, the competent lifting theorem relates very much to that. The lifting is an extension to an object who lives in a bigger space, and you preserve a certain structure. So if the pieces A, B, C have a certain structure, you want to lift it to preserve that structure. And you can do it sequentially. And then you can show, so you can do this in absurd generality. The A, B, and C could be operators. But if you understand how to do this for 2x2 matrices, and I always give that as an example to first year linear systems class, just to work on it with,
Start playing with those tools.
Start playing with those tools. Because if you write down, let's say I give you A, B, C, and the D is an unknown, and you say, what's the condition for this matrix to have norm less than 1? So if you write it down, then you see that you get an expression which is quadratic in D.
Okay. Yeah.
And it's very easy to check.
Yeah.
Is this... Basically, that's what you do, it except at the level of operators. And sometimes you put also structure. And the lifting has to do with some causality structure existing at some level, and there's an isometry, and then you lift it to something which is unitary. So you can go both ways, and you have a nice representation.
Yeah. Okay. Talking about causality. This is the next thing that I have in my agenda, if you want. So, okay, we've talked about the gap metric and this work that you had with Malcolm, 1990. Of course, you continue working on those threads of research, but something that really struck my interest and I really want to talk about is the arrow of time. So,
yes.
1995, I see this paper, Intrinsic Difficulties in Using the Doubly Infinite Time Axis for Input-Output Systems Theory, again with Malcolm Smith,
Yes.
on transactions of automatic control. What's the problem with the arrow of time?
Okay. So, again, this is a long story. We'll follow it up later on with some more things. This paper was a short paper. It's truly elementary, and it fits with a graduate course in, let's say, Fourier methods. The paper basically says the following, that the moment you look at stability from a controls perspective, you have to work with the positive real axis. You have to be using Laplace techniques, not Fourier techniques. And there's a very good reason for that. And it was more like a critique to the behavioral model of Jan Willems.
Yes.
And that sort of...
Because the time axis matters.
Yeah, the time axis matters. And that precipitated a lot of discussions, a lot of follow-up. So basically the idea is the following, that if you want to have the two-sided time arrow, the time axis, so you are prepared to see your input starting at minus infinity, you have a little bit of a problem, because at minus infinity, for an unstable system, a zero input can create a behavior which starts coming back alive at any future instance. In other words, you might have some state building up and having an effect much later.
Okay.
So we have basically a very simple example that shows the following thing. We were talking about graphs of systems. So the graph of a system is stabilizable if you can find you have the graph of a system, and stabilizable if you find a controller whose graph is at a positive angle to the graph of the plant.
Yeah.
Now, if you allow the graph to include signals that go back all the way to minus infinity, you can't do that. Because you can get the graph of a system, the closure of the graph could be open, and the closure of it contains a signal which is anti-causal. In other words, in order to handle it, you have to have anti-causal response. So somehow you bump it then against causality.
What does it mean to be causal, just for our audience?
So causal means like you will have a response that the output is non-zero before the input is non-zero.
So you need knowledge of the future, basically.
Knowledge of the future, yes. And the reason is because you can have an input that makes an infinitesimal bump at minus infinity, and that starts off a response of an unstable system. So if I have an unstable system, let's say 1 over s minus 1. Now, what is 1 over s minus 1? It's just a rational function, right?
Yes.
So you tend to think of it as some sort of a representation of a differential operator. Let's say the derivative of x or y, the output derivative of y is equal to y plus the input u. Now you have to pick your poison. You have to decide what kind of signals you are allowed in your framework.
Yes.
So if your signals start at a definite point in time, it's one story. If they start at minus infinity, it's another story. So the differential equation y dot is equal to y plus u has a solution which is admissible. It satisfies the differential equation, which has the input being 0 all the way to the origin and doing something afterwards, and the output starting at minus infinity, right?
Yeah.
And you can easily construct such a pair. So you have to decide whether this pair is legitimate for your system to be in the graph or not. Clearly, you don't want that, because this is, the system that can respond this way is non-causal, because it creates a non-zero output before the input materializes. So the output needs to know the future. So if you throw this pair out, then your graph is open, it misses a point, and then you cannot stabilize it.
Okay. So the only stabilizable plants are the stable ones.
Or the stable ones, yes.
Which is a bit disappointing.
It's disappointing, yes. Right. So you don't want a theory that says that.
Okay.
So
how do we fix this?
That paper was a critique. That you basically have something that we know from the times of Bode, Nyquist, and everything, that you use Laplace transforms. You start at a definite point in time. Stability has the time arrow built into it. So you have to have a start.
The very definition, basically, of stability.
Yeah, it's part of the definition. You have to impose that.
Because you want something to be preserved over time, starting from a certain point.
So again, this paper is a critique to a certain way of developing the theory.
So do we need a new notion of stability? Or
No, everything is fine. Everything is fine.
Okay.
It was just simply, you see, again, Jan had a very good point. Who tells you what are the inputs, what are the outputs, and look at the behavioral framework. But you have to be a little bit careful about how do you define stability. But again, we pursued the time arrow further in some later work, which is also very, very interesting.
Strongly suggested to all of our audience to read Feedback Control and the Arrow of Time, 2010, again, a paper with Malcolm Smith. There will be a link in the description. Yeah, one of the messages that I got from reading that paper is basically that, also the gap metric itself. So how we measure distances between systems is affected by the arrow of time.
It's affected by the arrow of time.
So if we reverse time, and you have a fantastic example on how to ride a bike, either in forwards time or backwards time, changes things dramatically.
Yes. Let me again, there is some theory in that paper, and there are some technical results that are very interesting, very intriguing. But I think the most interesting thing is the following, and this whole development relates very much to Carl Ostrom, that was interested in riding bicycles forwards and backwards. I don't know if you...
I was not aware of this.
Yeah, Carl Ostrom, and there were some other people looking at the time. We referenced this paper there. Tries to explain why the bicycle is easier to ride it forwards as opposed to pedaling backwards. But so let me explain a little bit about the dynamics of the bicycle, because that brings a very interesting point that has to do with thermodynamics, the arrow of time, and everything.
Okay.
So the bicycle, we all know, you steer the front wheel, and when you're riding as normal, riding forward, if the bicycle tilts, in order for you to stabilize it, you turn the steering wheel into the fall to move the base of the bicycle under you, very much like we stabilize a pendulum. If the pendulum tilts to the right, you just move the finger that you're holding the pendulum to the right to bring the base under and stabilize it. That's how the bicycle is stabilized. So when you're moving forward, everything is simple. If you tend to fall to the right, you turn the steering wheel to the right and the other way around. Now, imagine that you're pedaling backwards.
Okay.
When you tilt to the right, then you have to turn the steering wheel again to the right so that the whole angle of the bike starts turning and the wheel that is stiff has to come under you.
Yeah.
This is a non-minimum phase behavior because by the time you turn the steering wheel to the right, then you exacerbate the fall before you correct it.
Yeah.
So there is, for a short amount of time, you have to make things worse before you make it better.
Yeah.
And that's a sort of manifestation of a non-minimum phase behavior. You have a non-minimum phase 0.
Yes. An unstable 0.
An unstable 0. So going in one direction everything is fine because the 0 is stable. Going in the other direction is not fine because the 0 is unstable.
Okay.
The position of the 0 depends on the speed of the bike. There is a critical speed where the dynamics of the bike couples with the unstable 0 and the bicycle cannot be stabilized because you have a pole 0 cancellation in the right half plane. So going backwards, if you pedal very slowly, it's very difficult to ride the bike.
Yeah.
There is a critical speed that you cannot ride it at all. If you pedal even faster, then it becomes easier. So you have to accelerate and go past this hump, the difficult point, then everything is fine.
Amazing.
But there is a critical speed that going backwards, you just cannot do it. It's non-stabilizable.
Okay.
Now, what is the interesting thing here? The interesting thing here is that if I play a video of someone riding a bike, and actually I made a video.
Okay.
If you had a visual, I could have shown you. So we
can probably put a link, but
yeah, that's okay. That's okay. So let's say you have a bicycle and you're riding it, and you take the video of the bicycle, and now I can play the video forwards or backwards. In the video, I can have a metronome, so you know the speed. I can have markings of the ground, so I know exactly the speed of the bicycle. I know exactly the dynamics of the bicycle. And I ask you, is the video is the rider riding forwards or backwards?
Yeah.
Because I could have been riding forwards and play the video backwards in time. So the question is, does the video have a stamp of the time arrow in it? Let me explain this a little bit more. Let's I take a glass and I smash it on the ground.
Yeah.
I take a video and I play it forward. You see the glass smashed on the ground.
Yeah.
I played backwards and you see the shards coming back into a glass. And I ask you, what is the correct time arrow? Immediately, you know.
Yes.
Now you look at the bicycle, and the claim is that a control engineer will be able to tell, but a physicist will not. Because you really need to know exactly the subtle point about pole zero cancellation in the right half plane. You need to do the computations to see is the speed the right speed, the critical speed. And if it is the critical speed, then there's only one way that you can ride the bike, not the other.
And you're talking about physicists not being able to do that because the laws are time symmetric.
Yes, I mean, by looking at the video,
there's no difference, basically.
There's no difference. The difference has to do with the fact that the bicycle has to be ridden by a human who is effectively controlling it.
Yeah.
And the feedback loop in one time direction is permissible and the other is not.
Yeah.
So this touches upon the subtle point of the time arrow and feedback control.
This is amazing. And what about thermodynamics? Because then you mentioned this is related to thermodynamics.
It relates to thermodynamics because, at the heart of this whole thing is the information processing of closing the loop. It's not such a simple matter. So again, it's a long story, and some of this has not been written quite. So there are interesting sort of philosophical questions after this.
Which, is also occupying a lot of your late works, I imagine, because you're talking about energy harvesting lately and
definitely
stochastic optimal control and connections between thermodynamics. So we covered a lot of ground, Tryphon, today. I think we will have to end it here, but our audience can look forward to the second part of this episode, which will be about, let's say, your future endeavors in research.
Absolutely. Thank you very much, Alberto. It was a pleasure, and I've been delighted. It was a wonderful conversation.
Thank you for listening. I hope you liked the show today. If you enjoyed the podcast, please consider giving us 5 stars on Apple Podcasts, follow us on Spotify, support on Patreon or PayPal, and connect with us on social media platforms. See you next time.